This is the last of a series of videos on hypothesis testing using parametric tests, and we know now how to estimate the variance of a population and define its confidence interval. We also know now how to do a one-sample test of variance against the variance of a known population. In this video, we'll talk about how to test differences in variances of two sampled populations. And this is section 2.2.2.4. So this is our two sample test of variance. Okay, we have two samples from two different locations or something, and we want to know whether the variance of the first population sampled is different or well, if it's equal to or not equal to the variance of the second population sampled. Okay, and so we would, if say our measured variances are S1 squared and S2 squared, and to compare those, what we will do is take the ratio of one over the other. And remember, the variances, if they come from populations that are normally distributed, the variances will be have chi-squared distributions. They will be chi-squared variables. And it turns out that the ratio of two chi-squared variables will have a known distribution, and it will have an F distribution. So the ratio of these two will define our parameter F. And we're using F because it has a known distribution. And it looks visually similar to a chi-square distribution in that it starts with, it can't be less than 0. This ratio can never be less than 0. And it goes to some positive value. So the horizontal axis is F. And again, the vertical axis is the probability density function. And it's skewed on one side and has a long tail on the other side. Okay, so to test whether so you can see that near the hump is the probable range of F. Oh, and before I go into that, I wanted to mention that F depends on the degrees of freedom of the first sample and the second sample. So whereas chi-squared only depended on the degrees of freedom of one sample, the shape of the F curve will depend on both degrees of freedom. Okay, going back to our test. So if F is within this probable range, then the population sampled have the same variance. Okay, so F actually describes the ratio of two samples having the same variance. Okay, so if it's in the probable range, then the two sampled populations are likely to have the same variance. So the test will involve looking in either these two corners, two tails, for the improbable values of F. Now you'll notice that because the tail on the right-hand side is longer than on the left-hand side, we have a better resolution. A large change in F is a small change in the probability. So it's better to define F as being greater than 1. So we do that by if S1, if the variance of the first sample is greater than that of the second, then F will equal S1 squared over S2 squared if the second variance is greater than the first, then we'll define F as S2 squared over S1 squared. So we're always going to test whether the value of F falls in this right side tail. And so this right side tail will define the area under that will define the alpha. That will define our level of significance. Okay, so say we do some cores of tin sleep sandstone. This is an example taken from Davis's textbook, and we measure S1, the variance of porosity in percentages as 0.46, 30.46, and the variance of within our second core of the porosity of 23.21. And our null hypothesis is that the porosities of the two cores have the same variances, with the alternative that they have different variances. Okay, so step B, as always, is first to define our level of significance, and that's 5%. And then now we need to define the critical values of F. Well, it's really the critical value. There's only one value of F that's critical here. Okay, so again, we're looking, we need to find the critical value of F being at that which bounds the area of alpha to the right with the degree of freedom 1 in the numerator and degree of freedom 2 in the denominator. And so, okay, so we're going to define, okay, so F is going to be, I guess we're getting a little bit of ahead, working on the next step, but we need the next step to know which value goes on top. So F is equal to S1 squared over S2 squared. That's equal, because S1 is, the variance of the first sample is greater than that of the second, so we'll put that one on top. And that ratio is 1.312. So nu 1 is going to be the numerator degrees of freedom, and nu 2 is the denominator degrees of freedom. So let's look at our F table. That's not our F table. F table. Okay, so this table gives the value of F corresponding to the right tail, and this says alpha over 2, but I'm going to correct this. This should be alpha. Okay, so the numbers here, the numbers in the columns show the alpha values. The tables show the values of F. Okay, and so the columns show the degrees of freedom in the numerator. And in our case, we had 9 degrees of freedom in the numerator. Oh, I didn't tell you that, did I? I should have told you that. That was equal to 9. And we have 9 degrees of freedom in the denominator. And so we look for 9 degrees of freedom in the numerator. And this particular table doesn't have 9, but so let's just pick the next one, 8. And the degrees of freedom in the denominator is 9, and we're looking at the 5% significance level. So that's 3.23. That's our best estimate from this table. So F 5%, 9, and 9 is equal to 3.23. So what we find is that our calculated value of F is less than 3.23. So the ratio is not in this right-hand quadrant, it's in the left-hand quadrant. So we are left to conclude that we cannot reject the null hypothesis. Okay, and there's how you do a two-sample test of variance.